Okay, let's start. So it's a great pleasure today to have David Mitrouskas from IST, and he's going to talk about the low energy properties of a strongly coupled polaron. David?
So thank you, Daniel, for the introduction, and thanks, of course, to all the organizers for the invitation. So it's a great pleasure to have the opportunity today to share this talk with you about the low energy properties of the strongly coupled polaron. So this first slide is for those who want to have a physical picture behind the model that I want to discuss. And the polaron model is a model for an electron moving through an ionic crystal, and due to the electric charge of the electron, it polarizes the material by distorting the ions from the equilibrium positions. And as a consequence, these ions start to form small electric dipoles, which then act back onto the electron. And so this is really a combined system of an electron and a field, where the field is the polarization field of the material. Now, in the mathematical model that I will introduce, you will not see this microscopic crystal structure anymore, because this is a model of the so-called large polaron, where the wavelength of the electron is assumed to be much larger than the distance between these ions. So effectively, one zooms out of this microscopic crystal picture and then describes the polarization field really as a continuous quantum field. Now, the talk will consist of two different parts. In the first, where we consider two different so the talk will consist of two different parts, but we'll focus on two different versions of the polaron model. In the first part of the talk, I'll focus on the situation where everything is restricted to a bounded domain omega, and where we explicitly assume that translation invariance is broken. And then in the second part, I'll turn to the more traditional translation invariant polaron model that is defined on the full space. So the model describing this physical picture is known as the Fröhlich model, which goes back to the 1930s. So this really comes from the early days of quantum mechanics. And it's defined by its Hamiltonian, which is a linear operator on a suitable Hilbert space. So let me walk you through the notation here. For this confined version of the model, we choose a bounded domain omega and then describe the kinetic energy of the electron in terms of the Dirichlet Laplacian on this domain. And as I said, there are two components, the electron and the quantum field. So the Hilbert space is the usual L2 space for the electron with coordinate x, and then we tensor that with the Fock space, with the bosonic Fock space over L2. And let me mention that the excitations in this Fock space are usually called the phonons. And the Hamiltonian now consists of three different terms. So here we have the kinetic energy of the electron, and then there's the free field energy, which in this model is simply given by the number operator that I've written here in terms of pointwise creation annihilation operators with an index y, and this index y refers to the position of a phonon. And then so this operator counts the number of phonons in your quantum state, and you can also interpret it as the energy of an infinite collection of harmonic oscillators, each placed at a different point in space. And then there's a third term that describes the interaction between the electron and the field that is given by this linear field operator that creates or annihilates a phonon with an x-dependent phonon wave function v. And this v is called the form factor, and in the polaron model, it's chosen as the kernel of this operator here. And this is motivated by this physical picture of having an electron in interaction with these small dipoles. And the model comes with a single dimensionless parameter called the coupling constant alpha. And here I've chosen units such that this parameter appears as a 1 over alpha in front of the interaction and as a 1 over alpha squared in front of the field energy. So the energy of one phonon is actually 1 over alpha squared. Now in the literature, you will often find that the coupling parameter is absorbed into the definition of the creation annihilation operators. But here I prefer to keep them always as these precise, as these explicit prefactors everywhere. In particular, I will assume that the creation and relation operators always satisfy the usual unscaled bosonic canonical commutation relations. And throughout the talk, I will also use the following shorthand notation, in particular for the field operator and the number operator. But keep in mind that this field operator really acts on both systems, the electron and the quantum field. And just as a small technical remark, note that this expression is somewhat formal if directly interpreted in terms of an operator. And the reason for this is that this form factor is not a function in L2. However, due to a nice commutator trick that goes back to Lieb and Yamazaki, it is defined as a semi-bounded and enclosable quadratic form, which then gives rise to a unique self-adjoint operator. The precise characterization of the operator domain, however, is a bit more tricky, and this would require a more careful analysis. Now, for this model, we're interested in the spectral properties in the so-called strong coupling limit. And to see that large values of alpha really correspond to strong interaction, it's important to keep in mind that we have this small prefactor in front of the field energy. And this implies that for large alpha, your quantum state is allowed to have many phonons. And this is why this field operator, this interaction, will be also of order 1, so of leading order in this limit. Now, the motivation to study this particular confined or bounded version of the Polaron came from a recent work by Rupert Frank and Robert Saringer, where they proved the following statement, namely that the ground state energy of this operator has a two-term expansion of the following form, where we have two alpha-independent explicit constants that are both determined by the semi-classical Polaron model, which I'll introduce on the next slides. And the main result that I want to address in this first part of the talk is an extension of this result in two directions. A, we want to extend it to other eigenvalues than the ground state energy. And B, we want to give a more accurate description, precise description of these eigenvalues by including also higher order terms to these first two terms. So it turns out that there's an effective theory for the Polaron at large coupling, which is in fact a semi-classical theory, where the field is now classical, but the particle remains a quantum particle. The electron remains a quantum particle. So in this semi-classical energy, we still have a wave function psi for the electron, but then the field now is classical. So wherever you saw a creation or relation operator on the previous slide, it's now replaced by a real valued field phi of strength alpha. So in particular, this semi-classical energy now is completely alpha independent. And if you fix the electron function psi, then this is of course a quadratic functional in phi. So here it's linear and here it's quadratic. And we know how to minimize a quadratic functional by completing the square. And if you insert the optimal field configuration, which I denote by phi p, then we arrive at the so-called Pk functional for the electron. And this Pk functional contains this attractive self-interaction. So in the semi-classical model, we now have an electron with an attractive density-density self-interaction via these Coulomb-type kernels. And throughout the first part of the talk, I will always assume that this Pk functional has a unique normalized minimizer, and we call the minimal energy the Pk energy, denoted by EP. And we shall further assume that whenever we are away from the minimizer, then we have a quadratic lower bound of the energy in terms of the distance to the minimizer. And these are really two implicit conditions on the bounded domain omega. But thanks to a paper by Dario Feliciangeli and Robert Saringer, we know that these two conditions are both satisfied, at least if omega is a ball of some fixed radius. And then let me also mention a work by Correggi, Falconi, and Olivieri, where they study similar confined Pk-type functionals. Now, the Euler-Lagrange equation to this minimization problem reads as follows, where Hp is a Schrödinger-type operator with an external potential that's created by the classical field. So here the picture is that that the electron is caught by its own polarization field and then sits in the lowest energy level of this Schrödinger operator. And for convenience here, I've subtracted a suitable energy so that the lowest eigenvalue of this operator HP is indeed 0. And by capital P, I will denote the orthogonal projection in the electron coordinate onto the ground state of this Schrödinger operator HP, and by Q, the projection onto the corresponding orthogonal complement. And now we've seen where the leading order Pk energy comes from. So let me go back to the first slide. So now we've seen where the first term in this expansion comes from. And to understand the second term, we have to introduce the operator H that describes the quantum fluctuations around the classical field. And at this point, it becomes a bit more convenient to explicitly extract the leading order of the contribution, the large contribution of the classical field from the Hamiltonian. And this, as usually, can be done in terms of this of a unitary Wild transformation. So after subtracting the Pk energy from the Hamiltonian and applying this transformation, we obtain the following Hamiltonian, where this Schrödinger operator HP from the previous slide appears, and where the form factor now is shifted by the classical value of the field. And the main point of this transformation is that since it extracts the leading order of the energy, and since this operator HP has a lowest eigenvalue 0, we can now at least formally think of these two terms here really as perturbations of this operator HP. And here you can already see an interesting feature of this problem, namely that the unperturbed part of the Hamiltonian only lives on the electron subspace. Now, one way to introduce the quantum fluctuations is to consider a block diagonalization of this operator H alpha. And if you assume for a moment that everything is well defined here, then this block decomposition or block diagonalization is simply an algebraic identity. And this entry here is usually called the Fesch-Barschur complement. And due to the fact that this P projection, so it's a block diagonalization with respect to this operator P and Q that are introduced here, sorry. And this entry here is usually called the Fesch-Barschur complement. And due to the fact that this projection P is a rank 1 projection, but only in the electron coordinate, this Fesch-Barschur complement now lives only on the Fock space, and is of the following form. So we have again the number operator, and then here we have this partial expectation value of this operator in the electron Pk minimizer. And now due to the presence of the inverse of the full Hamiltonian here, when restricted to this Q subspace, this Fesch-Barschur complement is still a very complicated object. However, if we replace this inverse of the full Hamiltonian by the inverse of the unperturbed part only, again when restricted to the Q subspace, then we obtain a much simpler Fock space operator that I denote here by math script H. And in fact, this operator H is now a quadratic Bogoliubov type operator, and by that I mean that it's quadratic in creation and relation operators as written here, with a kernel function f that one can explicitly determine from the previous definition here. And the motivation for this definition of H is that the difference between the complicated Fesch-Barschur complement here and this quadratic operator H is at least formally of subleading order. And that you can easily see by applying the resolvent identity to the difference of these two inverse operators. And here I say that this is only formal because these are, of course, all unbounded operators, but it turns out that the remainder will be, in fact, small once it's tested against suitable low energy states of the system. And now using the fact that this is a quadratic operator, we can, of course, study its spectrum very explicitly. So in particular, one can find a unitary operator, so-called Bogoliubov transformation, that relates the operator H to the second quantization of an explicit one-body operator A. And here it turns out that the spectrum of this one-body operator A consists of discrete eigenvalues between 0 and 1 that accumulate at 1. And with this information, we can, with this information, now the eigenvalues and eigenfunctions of the operator H are simply those of a free Bose gas of particles of bosons with energies and eigenfunctions determined by the one-body operator A. So in particular, the eigenvalues can now be written in terms of these combinations of eigenvalues of the operator A. And with this, we can state our first result that comes from a joint preprint with Morris Brooks. And the theorem states that every eigenvalue of the Fröhlich Hamiltonian has a two-term expansion in terms of this semiclassical Pk energy, and then the corresponding eigenvalue of this quadratic operator H that describes the fluctuations of the field around its classical value. And what I said so far already contained the essential ideas also for the proof. So we established this asymptotics by deriving upper and lower bounds for these eigenvalues. And in particular, for the lower bound, what we do is we first prove that the Fesch-Barschur complement is indeed well defined. So this requires in particular that we show that the full Hamiltonian, when restricted to this Q subspace, so away from the Pk minimizer, has a bounded inverse. And the block decomposition then gives immediately a lower bound of the full Hamiltonian in terms of this Fesch-Barschur complement. And to study the spectrum of the Fesch-Barschur complement, we then use so-called Fock space localization techniques, in particular to compare it with this explicit quadratic operator and to show that the remainder is of subleading order when we evaluate it in suitable low energy states. And as already said, this extends the first result by Frank and Zaringer to other eigenvalues than the ground state energy. And the conceptual novelty of the proof was really to use this block diagonalization and the Fesch-Barschur complement to study the quantum fluctuations around the classical field. And note in particular that the statement provides quantitative control over the spectral gaps between these eigenvalues. And this will be important for the proofs of the next theorem, of the next two theorems, where we discuss higher order contributions to these first two terms in the expansion. So in this second theorem from this joint preprint with Morris, we extend this expansion to higher orders. And the statement is that for every eigenvalue of the Fröhlich Hamiltonian, there is a sequence of alpha-independent coefficients such that you can expand the eigenvalue in terms of an asymptotic series in 1 over alpha. So here we have the eigenvalue, and then we have the first two terms that come from the previous theorem, and then there's a series in 1 over alpha up to any order in 1 over alpha, and a remainder that's of smaller order. And the right way to read the theorem is that you first fix the desired order B, and then you have to take alpha large enough so that the remainder is smaller than any term on the left side here. And to define these coefficients, let us fix the number n and assume for simplicity that the eigenvalue of this quadratic operator H is non-degenerate. And then we call its eigenfunction, let's call its eigenfunction gamma. And for notational simplicity, let us also drop this superscript n on this slide. And then we introduce the spectral projection that projects away from this eigenstate gamma. And since we know that the quadratic operator H has spectral gaps of order 1, we can also define this inverse when we project away from this state gamma. And then we introduce a family of operators VL, where V1 is the shifted field operator, V2 is the number operator minus this eigenvalue of this operator H, and the VL, the other VL are just these shifted coefficients that we are still about to define. And with these operators, we now define yet another family of operators called here W, that are defined by this expression. And here we take again this partial expectation value in the Pk minimizer. So these are still complicated operators on Fock space. And the coefficients EL are now iteratively defined by these expressions, where we now evaluate these combinations of these operators. In the state gamma, there was the eigenstate of the operator H. And now, while the precise definitions may not be so relevant for the sake of the talk, the main point that I want to convey is that the definition of these coefficients really involves sort of two perturbations. So there's two perturbation expansion. So there's one perturbation expansion around the PK minimizer that's represented by this expression, and that gives rise to this resolvent R infinity. So let me go back. So this resolvent R infinity was the resolvent of the unperturbed part of the Hamiltonian. But then there's really a second perturbation expansion around this state gamma that then involves these operators here, these W operators, and the resolvents of this H operator. And the reason of this sort of twofold expansion is really the fact that the unperturbed problem of the Hamiltonian only lives on the electron subspace. That's what I kind of try to motivate by this formula, that the unperturbed part only lives on the electron subspace. And another way to view this is that the unperturbed part of the Hamiltonian does not fix the quantum fluctuations in the Fock space. And just one more remark here, that while these coefficients may seem still kind of complicated, in principle they can be computed fairly explicitly, which is due to the fact that the state gamma is given as an eigen state of this quadratic operator, so it's fairly explicit as I've written here, and also this action of these unitaries are very explicit, so in principle one can compute this very explicitly. Now, in the last result that I want to address for the confined Polaron, we want to say something more explicit about the B dependence of these error constants here. But before I come to that, I'll briefly review the main ideas of the proof of this statement. So the main idea of the proof is in principle very simple, and it's based on the construction of approximate eigenstates. So we consider states of the following form that are given in terms of this twofold perturbation expansion. So here we have one perturbation expansion of the PK minimizer psi p that's represented by this operator. Then there's a second perturbation expansion or perturbation ansatz represented by this operator here around the state gamma that was the eigenstate of the operator H. And these operators W and V are defined in terms of series of these operator VL and WA that I introduced previously. And the main point is that of this construction is that these states solve an approximate eigenvalue equation of the following form. So here we have the operator H alpha, and here we have the desired series approximation of our eigenvalue, and then we have a remainder estimate that is of lower order. And since we know that the spectrum of H alpha is discrete, then this type of inequality immediately implies the existence of an eigenvalue that has to be close to the eigenvalue lambda. So this is illustrated in this picture below here. So now we know that around these values lambda, there is a small window where the operator H alpha has to have an eigenvalue. And now we can combine this with our first result about the two-term expansion of the eigenvalues. And in fact, this two-term expansion already gives us sufficiently good a priori localization of the eigenvalues so that we can conclude that the only eigenvalue that's allowed to live in this small window around lambda has to be the nth eigenvalue of our operator. And now, since we know that the size of this window has to be is of the same order as this arrow here, we now know that the eigenvalue, the nth eigenvalue, is indeed given by this series expansion plus a remainder that's of lower order. And one of the technical difficulties that come up can be related to a remark that I made in the very beginning about the domain of this operator. And in fact, it turns out that that these type of states are not even in the domain of the operator. So this expression is not even well defined. And to solve this, one has to implement a unitary, so-called unitary dressing transformation, the Gross transformation, that maps these type of states into the domain of the operator H alpha. But of course, the presence of this unity then adds many new terms, and that makes the whole complication, the whole argument more complicated. So that's all what I want to say about the idea of the proof. And as I said before, in the last result I want to present for the confined Polaron model, we now want to address the explicit B dependence of these constants here. And to this end, we focus on the case where the eigenvalue of this quadratic operator is actually non-degenerate, which is in particular the case for the ground state energy. And in this case, we can now improve the previous theorem by deriving remainder estimates of the following form, and also by controlling the growth of the coefficients by these asymptotics. And now you can ask, of course, why this would even matter, because the series will diverge anyway. And the answer to this is the idea of Borel summability. And very roughly summarized, Borel summability in here would imply that we could recover the eigenvalue of the Hamiltonian in terms of the Laplace transform of this convergent series here. So the advantage of a Borel summable series is that you can really recover it in terms of a convergent series. Now, even though we can prove in this theorem these error estimates that are sort of typical for Borel summable series, the answer is still that we don't know. And the reason for this is that Borel summability in particular requires an analytic continuation of the eigenvalue to a certain domain, complex domain. And so far, it is not clear to us how to obtain such an analytic continuation of these eigenvalues. And it seems that one of the difficulties is again related to the fact that the unperturbed operator only lives on the electron subspace. So in particular, that the unperturbed eigenvalue problem is infinitely degenerate. And even though one can probably argue about the practical relevance of Borel summability, I think it would be mathematically a really nice result to really prove that these eigenvalues are Borel summable. And while we cannot prove this at this point, this was kind of the motivation to look at these improved error estimates. And with this, I'll conclude the first part of my talk. So if there are any questions, we can also have some questions now.
Yeah, can I ask a simple question? So I want to understand the physical motivation of this setting. So everything is confined, or the electrons are electron is confined in this region omega.
Yes, everything is confined.
What does this represent? Does it represent sort of small region that electron is confined, like a, I don't know, dot or some potential well or something like that?
Well, one could also choose to add to define everything on R3 and to add a confining potential to the electron or even a Coulomb potential. So I think that should turn out to be similar. I mean, we didn't really study this, but I think that the result would be similar. So the point here for choosing this confined region is really to break the translation invariance explicitly, which would be, I mean, much more difficult to study these questions in a translation invariant setting. So that was kind of the mathematical motivation. And I think there are physics papers where they study these systems with an additional confining potential for the electron, but we don't know if they do that.
Okay, thank you. So you're going to discuss translation invariance case?
Yes.
Second part.
Okay, so let's come to the more traditional polar model. This is the translation invariant Polaron in R3. And so here the Hamiltonian reads as follows. We have again the kinetic energy of the electron. and then the number operator that describes the field energy of the phonons, and then this linear field operator that describes the interaction between the electron and the phonons. And now this form factor is of this form, and this again corresponds precisely to this physical picture of having electron interaction with these small dipoles. And note that here I've chosen different units such that the coupling constant alpha now appears explicitly only at the square root of alpha in front of the interaction. And the connection to the units that I used in the previous model is really just a rescaling of all the coordinates by a factor 1 over alpha. In particular, note that I still assume that the creation and relation operators satisfy the usual unscaled canonical commutation relation. So that's the quantum model in R3. Now we can introduce again the semiclassical model in terms of this nonlinear Pk functional, where we have this attractive density-density self-interaction for the electron via this Coulomb potential. And in this case, it's known that the Pk function has unique minimizers, psi p, but only up to translations. So this goes back to a work by Lieb. And this effect is sometimes referred to as self-trapping, since we have a translation variant energy functional, but the ground states are localized at some point in space because they're caught by their own polarization fields. And then we introduce again the Pk energy as the infimum of the energy of these functionals, of this functional. And in analogy, we can also introduce the quadratic Bogoliubov type operator that describes the quantum fluctuations. And one observation that's not so relevant for the talk, but actually important for the proof, is that this operator H now acquires 3 zero modes that you can think of as the Goldstone modes that arise from the broken translational symmetry of the Pk functional. Now, an important feature of this model is that it's translation invariant, which implies that the Hamiltonian commutes with the generator of the translations, which is the total momentum operator. So here we have the momentum operator of the electron, and here I've introduced the momentum operator of the quantum field. And this further implies that there's a so-called fiber decomposition or a direct integral decomposition of the total Hamiltonian in terms of these fiber Hamiltonians H of P. And what happens is that we first go into the frame of the electron, so that kind of removes the electron variable from the interaction, but it shifts the electron momentum by the field momentum. However, since the expression then is independent of the electron variable, we can replace the electron momentum by the total momentum P. And since the electron now is sort of out of the picture here, these fiber Hamiltonians are naturally operators that act only on the Fock space. And with these fiber operators, we can now define the joint energy momentum spectrum in terms of all energies and momenta, so that the energy and all values E and momenta P, so that the value E lies in the belongs to the spectrum of one of these operators that describe the system at total momentum P. And in particular, we'll be interested in the energy momentum relation that is defined as the lowest eigenvalue of these operators, the lowest, the infimum of the spectrum of these operators in terms as a function of P. And now what does this picture look like in the non-interacting case? So we set alpha to 0, then as long as we are below momentum 1, so as long as P is smaller than 1, then we have an eigenvalue curve given by P squared. And this eigenvalue is in fact attained by the vacuum. So if you apply this operator to the vacuum, then the number operator and then also the field operator are both 0. So this just gives you the eigenvalue P squared. However, what you can also do is you can always add one phonon with momentum approximately given by P. So then this term becomes very small, and then the field energy gives you the energy 1. And these one phonon states lead to an essential spectrum that starts at 1 for each P, and then it fills the full line. And the aim of the rest of the talk is to explain how this picture changes for large values of the coupling constant. And then to get an idea of what the picture is, let me review a short list of known results, and that's not meant to be an exhaustive list of results about this on this problem. So first, the inverse curvature of this energy momentum curve at p equals 0, and that's also called the effective mass, and I'll come to that again in a moment, is always finite. Then a recent paper in collaboration with Jonas Lampert and Christoph Mischli, we showed that, and then also independently by Stefan Polzer, who use very different methods from probability theory, we showed that this energy momentum relation attains its minimum uniquely at momentum p equals 0. And then there are these two very classic papers by Donska and Baradan and Lieb and Thomas, who studied the large alpha expansion of the energy at p equals 0 and showed that it's given, again, in terms of the semiclassical PK energy, now multiplied with this large prefactor alpha squared, which comes from the fact that I'm using these different units here. And I think Donska and Baradan, they sort of proved the limit theorem by means of probabilistic methods. And then Lieb and Thomas, they applied more functional-analytic methods and then also managed to resolve the asymptotics of this error. Then there's this nice paper by Schach-Möller, where he used the HVZ theorem to study the localization of the essential spectrum of these operators. And it turns out that the picture is somewhat similar to the non-interacting case, namely that these essential spectra are p-independent, and they always start at the energy at p equals 0 plus 1, where this again corresponds sort of to a phonon that carries all the momentum p, but it's kind of placed far away from the electron, so it doesn't really feel any interaction with the electron. So then the picture is that we have this essential spectra here on the right that start again from the energy at 0, shifted by this one phonon energy. And then there's been this famous effective mass conjecture by Landau and Peker, and also by Herbert Schwan, which states that the effective mass, which again is defined as the inverse curvature of this curve at 0, diverges for large alpha with the rate alpha to the 4th power with an explicit coefficient given again in terms of this Peker minimization problem. And if you now take this kind of insight and also extrapolate the effective mass conjecture to larger momenta away from 0, then we arrive at the conclusion that the picture is qualitatively rather similar to the non-interacting case. However, quantitatively, the picture changes drastically. So for instance, the whole picture is shifted downwards by a very large negative energy that's proportional to alpha squared. Now the gap to the essential spectrum, that stays of order 1, so that's sort of similar to the non-interacting case. And again, if we extrapolate this effective mass conjecture to larger momenta, then we kind of get the prediction that we would still have a parabola, but that's now flattened really by a factor 1 over alpha squared. So whereas in the non-interacting picture, everything here lives on the order 1, here the parabola now really lives on this order alpha squared. And the physical picture is that this electron is surrounded by this cloud of phonons and gets so this kind of forms this quasi particle with a very large effective mass that it kind of leads to this very flat parabola here. And now the first result is from a paper with Christoph Mischli and Robert Saringer. We showed an upper bound for this energy momentum relation in terms of these 3 terms. So there's the leading order term that's again this semiclassical Peker energy, and this is the one that should be expected from this expansion by Donskoy and Varadan and Lieb-Thomas for the energy at momentum 0. Then there's an order 1 term that describes again these quantum fluctuations around the classical field in terms of this quadratic operator H. Then there's this third term that involves in particular this parabola with an effective mass that's precisely the one that you get if you extrapolate the effective mass conjecture to sort of the large momenta in this picture. And this one here corresponds to the region where the parabola already entered the essential spectrum. So then we know that the lowest eigenvalue in this region has to coincide with the bottom of the essential spectrum. And I don't want to say much about the proof of the statement, which is based on testing the energy with suitable trial states. But let me just mention that the difficulty that arises comes from the fact that we have to really fix the total momentum, right? So we have to work in this fiber picture that I introduced before. And the complication that arises is due to the fact that the semi-classical energy, so the leading order, really arises from the semi-classical picture. So in the semi-classical picture, the canonical states are these product states where we have the pK minimizer for the electron and then a coherent state for the quantum field. However, these states are certainly not states of fixed total momentum. These are superpositions of many different momenta, so they're kind of a wave packet, so to say. So now we have to fiber these semi-classical states, and the fibering makes already the derivation of the leading order challenging. But then we also have to include the corrections to get the order 1 correction, the quantum fluctuations, because in order to see this parabola here that lives in a window of order 1, we really have to see the rest energy, so to say, with the same precision. And this makes this in the end, this was a very long and subtle computation to get these terms here for the energy. And our matching lower bound was then shown later by Maurice Brooks and Robert Saringer. And now if you combine the upper bound and their lower bound, then you can conclude the following statement, that if you look at the energy momentum relation on its natural scale, which of order alpha squared, as you can see from the picture that I motivated in the previous slide, then this in the limit, this really corresponds precisely to this parabola that we expected. So we have this regime where we still have this quasi-particle with this very large effective mass. And then we have this, then once we cross the essential spectrum, then it's just given by the bottom of the essential spectrum. And what's important here is to note that with this, we cannot say anything about the effective mass conjecture. Right? So the effective mass conjecture was really about the inverse curvature. And here we prove upper and lower bounds. So we prove upper bounds, they prove lower bounds for this energy. So naturally, we cannot say anything about the derivatives. And another way to view this is that the errors in this theorem, they do not scale like p squared. So you cannot extrapolate to really small momenta. So the right way to read these statements is really that it gives an asymptotic formula for the energy momentum relation in the bulk of large momenta. Let me note, however, that the effective mass conjecture has been indeed recently solved in 2 papers by Maurice Brooks and Robert Saringer, and then by a very impressive preprint by Maurice that's just appeared on the archive last week. So in this paper, from Maurice and Robert, they prove an upper bound for the effective mass. So there they prove, so to say, the upper bound of this asymptotics. And then in this more recent preprint by Maurice, he managed to prove also the lower bound. And for completeness, let me also mention that there has been also a couple of recent results in the probability community regarding this effective mass problem. And together with this together with the asymptotics of the effective mass that has been established in these two papers, and with this result here, we now have a fairly good understanding of the energy momentum relation for large values of alpha. Now, the last theorem that I want to present, we sort of ask the question whether there may be whether there can be other eigenvalues between this lowest energy curve here and the bottom of the essential spectrum. And the answer is that yes, and in fact there is an unbounded number of such excited bound states between the bottom of the spectrum and the essential spectrum. So this is from a paper together with Robert, and there we show that when we restrict the momentum p, let's say away from this region here, then so we have to kind of look at the region. Yeah, so we restrict away from the region here, then the number of eigenvalues in the discrete spectrum is unbounded in the limit of large alpha. And then we kind of surprisingly found out that it seems that the existence of these eigenvalues has not been predicted in the physics literature. So we found even some papers that did some heavy numerics on this problem, where they also did not find the appearance of these excited bound states for this model. And that's probably the case. So to study this numerically, it seems kind of difficult because the number of degrees of freedom in your system is very large. It scales like alpha squared. And for that reason, it seems that the numerics that have been done so far sort of go roughly, let's say, up to values of alpha 10 to or 15. And apparently in that region, no such eigenvalues appear. So it's known from a paper by Robert that the discrete spectrum in the opposite regime, in the small coupling limit, really only consists of the ground state eigenvalue curve. So the picture now is sort of that there are no eigenvalues at weak coupling, and at some point, for some large value of the coupling, there will appear the first eigenvalue. Then if the coupling becomes larger, then there will be more and more eigenvalues, and then eventually they kind of accumulate at the bottom of the essential spectrum. And well, so far we can only prove the existence of these eigenvalues. We have a clear prediction where they should actually be found. And this sort of connects a little bit to the first part of the talk. Discuss this confined version of the Polaron. And so the prediction is that these eigenvalues should be actually found around the eigenvalues of these quadratic operators that describe the fluctuations around the classical field. So in a sense, you take the ground state curve that's given as shown here by this parabola, and then you have the ground state energy of this quadratic operator, and then you just shift the energy of the quantum fluctuations by the excited eigenvalues. So that sort of they all are predicted to have the same curvature as the ground state energy band. But in the translation invariant setting, this question seems much more difficult than the confined case, and with the method so far, it does not seem to be a consequence of the methods that we have so far. And with that, let me conclude. Let me make a short conclusion. So we investigated the confined Fröhlich Polaron for strong coupling. We proved an asymptotic series expansion for the low energy eigenvalues of the confined Polaron model. Then we investigated the energy momentum spectrum for the translation invariant Fröhlich Polaron, and we showed that on the natural momentum scale of order alpha squared, the energy momentum relation in fact has a parabolic shape that's kind of determined by the Baker mass. And as a last result, we showed that the number of excited eigenvalues between the ground state energy curve and the bottom of the essential spectrum is in fact unbounded in the strong coupling limit. And now let me just mention that one can study corresponding or similar problems also in the time-dependent setting. And here one can kind of derive the so-called Landau-Pekar equation. It's a set of two coupled nonlinear PDEs for this semi-classical system of an electron and a classical field. And then here kind of the goal was to derive these Landau-Pekar equations in the strong coupling limit, starting from the microscopic time evolution of the quantum system. And that was done a couple of years ago in collaboration with Nikolai Leopold, with Simone Rademacher, with Benjamin Schlein, and then also with Robert Zeiner. And with that, I'll thank you for your attention.
Many thanks, David, for this beautiful talk. Are there questions? So please unmute yourself and just ask the question. So otherwise, I have one question. So at the beginning, you discussed the confined model, yeah, and then the one of the whole of R3. There is no way to try to get the one as the limit of the other. So for instance, if you're taking, for instance, a torus for the first the confined model.
So in the confined, so first it was important in the confined model that there is no translation invariance. So a torus with periodic boundary conditions would not, so the methods would not extend to this setting. But regarding the limit, let's say a large volume limit, I think is what you're having in mind. I mean, they will not work because with our result, they will not work because all these constants
they depend on omega.
So the volume has been really fixed here, and I mean, I don't know. Certainly, there are some quantitative estimates, so one could see how they depend. But certainly, these constants will explode with the size of the volume.
Yeah, thank you. Other questions?
Yes, I have a question. Can you hear me?
Yes.
Yes, Wojtek. Yeah.
So I'm wondering who actually proved this Pekar conjecture, Brooks and Zeiringer, or probabilistic people?
Oh, okay. So I think in this recent works from the probability community, they managed, I think the most recent result managed to prove a lower bound that shows the quartic divergence, but not with the right constant. So that I think is the most recent result from the probabilistic community. And there have been results prior to that, which kind of showed a little bit weaker rate than the alpha 4. So, and I think now it has been established using mostly these analytic techniques. So Morris and Robert, they proved an upper bound for the effective mass. So they proved this an upper bound. And what they did, in fact, is they used the lower bound, that's the one that matches this upper bound, which, I mean, a priori has nothing to do with the effective mass because it is not, I mean, it doesn't say anything about small momenta because the error really does not scale as p squared. But then what they did, and that's why I wrote here via Polzer, then they used a very nice result in this paper from Stefan Polzer, and then there's kind of a sort of concavity result of the energy momentum relation that allowed them to extrapolate the lower bound really to p equals 0. And that sort of gave the upper bound for the effective mass. And then the lower bound of the effective mass, so this is a lower bound, that was published last week in a preprint by Morris. So I think these two together that resolve the conjecture by Landau-Pekar.
Okay, thank you.
Thank you. Other questions?
Yes. So you discovered this unexpected excitation energy in this translation invariant case. Yes. Do you see anything corresponding to this in this confined case? You had rather detailed results in confined.
Yeah. I mean, in a way, these are one could say that these are exactly these correspond to excited state. So that's really, so let me go back here to this first two-term expansion. So in this confined case, these eigenvalues are really given in terms of this Pk energy and these eigenvalues of this quadratic operator that describes the fluctuations around the classical field. And of course, there's now no momentum term. I mean, there's no momentum, concept of momentum here. But our prediction is that these eigenvalues, let's fix the momentum to 0. So that's in the method momentum 0. Then these excited eigenvalues should be exactly these eigenvalues, given by the Pk energy, and then these eigenvalues of this quadratic operator that is very analogous to the confined case. I mean, formally this looks, we expect the same, but here it seems much more complicated to really get control of these asymptotics for the eigenvalues.
Does this analogy help understanding the sort of physical nature of these excited states? Or, I mean, you said physicists didn't know about this.
Yeah, I mean, we were kind of surprised that we couldn't find it. Again, I think in these numerics that we found, probably the reason that they didn't see them was that the analysis was kind of restricted to relatively moderate values of alpha. So I think they kind of up to 10 and 15. Now, I mean, physically, the physical picture that you have is really that these excited, so you have kind of the same quasi-particle, right? If you interpret this parabola as a quasi-particle, then kind of the form of the parabola doesn't change, right? The excitation energies here are not p-dependent. So you can really think of this as internal excitations in this phonon cloud that surrounds the electron. Okay, so it's kind of internal excitations, I would say. That's our physical picture of these.
So this picture tells you that you can understand this by studying these confined models. Okay, thank you.
Thank you. More questions?
Then maybe let me follow up on this question of Hall about this picture, which we now see. Can there be crossings of excited levels, or is it excluded?
So this is really, so don't take this picture too serious. I mean, this is kind of our prediction how these eigenvalues would look like. At the moment, we only know upper bounds for the eigenvalues in terms of these curves. So that's sort of how we prove the statement. We find a family of states or subspaces so that they have the energy below these curves. So that's how we can conclude that they exist, because they live below the essential space. But the precise curve, asymptotics of these curves, we don't know yet. But we don't expect that they cross, because we expect precisely that they're given in terms of the ground state energy curve, and then shifted by these momentum-independent excitation energies of the quantum fields. So we would not expect that they actually cross.
That would be interesting to exclude crossings, because they cause a lot of complications in Moore theory, in scattering theory, and such things. Do you know anything about possible excited states embedded in the continuum?
That's a good question. No, I don't know anything, but I mean, one could imagine that. So I said that, I mean, this whole discussion kind of revolves around the starting point that the electron is in this lowest eigenvalue of this Pk, right, in this classical polarization field. And that, of course, sets the leading order energy. I mean, once you excite the electron out of the state, you really modify the leading order of the energy. And if you so let's go here. So but the leading order of the energy, I mean, is much larger than the spectral gap to the essential spectrum, right? So whenever you start to excite the electron out of this Pk ground state, then you would definitely be in the continuum. But that I don't know if somebody has studied whether these actually may correspond to embedded eigenvalues or something. But that would be kind of my idea, that you could probably excite the electron out of this Pk ground state, but for that we have not done so far.
Okay, thanks.
Thank you. Yet another question. If not, everybody can unmute themselves and we can thank David for this beautiful talk. Now we can stop recording.